All right, guys. So finally, we'll get started. So we're doing problems from chapter 14 today. Okay. So the first problem is when the current in one coil changes at a rate of 5.6 amps per second and EMF of 6.3 millivolts is induced in a second nearby coil. Okay, so this is a mutual inductance problem. What this is you saw that if you have a circuit here and if a current changes in circuit 1, it'll induce an EMF in circuit 2. And why does it do that? Because this current is producing a magnetic field there, and that magnetic field is changing in the second coil, and that induces an EMF. Okay? So let me... So here's circuit 1 and circuit 2. Okay. So the equation is the EMF induced in circuit 2 is proportional to the rate of change of current in circuit 1. Okay. And now the sign tells you the direction of the EMF. Right now we're not interested in that. So the magnitude of the EMF is M12 magnitude of di by, okay. All right, so the value of mutual inductance is what we want to find. Okay. So the magnitude of the induced EMF times rate of change of current. Okay. So the induced EMF is 6.3 millivolts, and the rate of change of current is 5.6 amps per second. And mutual inductance is measured in henries. Okay. So that's the units for the inductance. Henries, so 1.125 millihenries. Okay. And again, you guys remember, this number depends on the proximity of these two circuits. The closer they are, the bigger this number will get. Okay? All right. And so in general, you don't have a closed form expression for this. It depends on, so for instance, even at the same distance, if the orientation is like this, the mutual inductance changes. Okay? So, okay, so here's a problem where we can get you a closed form expression. This says a 600 turn solenoid is 0.55 meters long, half a meter long, about this long. Okay. And 4.2 centimeters in diameter. 4.2 centimeters, that much. Inside the solenoid, a small 1.1 centimeter by 1.4 centimeter single turn rectangular coil is fixed in place with its face perpendicular to the long axis of the solenoid. What is the mutual inductance of this system? Okay. So here's the solenoid. This thing is wound with wire. Okay. Inside, we'll place a coil like that, a rectangular coil like that. And so there's the magnetic field inside the solenoid. The magnetic field inside the solenoid is mu naught Ni. So, and oops. So, and the EMF induced in the coil is given by dphi by dt. This is Faraday's law. Okay. So we'll call this 1 and this 2. All right. Well, and the, okay, so the EMF in coil 2 is that EMF in coil 2 is minus d phi d by dt is, okay, the magnetic field times area of coil 2. Okay. The magnetic field is d by dt is mu naught n I1 A2. All right, again, this solenoid is producing a magnetic field inside, and that magnetic field is threading this coil. And now what we'll do is we'll change the current in coil 1, so the magnetic field changes in coil 2, and that's inducing an EMF in coil 2. All right, so that's what this is saying. So E2, and what is changing? N is not changing, area is not changing, only I1 is changing. Okay. So it's minus mu naught N A2 d by dt of I1. Okay, so
because I1 is only changing, then that is the only one being affected by the
derivative, yeah. Mm-hmm. Yep. Okay. So you see, if you compare this to this expression, see, EMF in coil 2 due to change in current in coil 1. That proportionality constant is M12. So in this expression, that would be the mutual inductance. Okay. Okay, so the mutual inductance M12 is mu naught N A2. Okay. So the mutual inductance depends on the number of coils per meter on the first solenoid, first circuit, and the area of the second circuit. Okay. So for this particular configuration, we were able to calculate that. In general, you don't have a closed form expression like this. Okay. All right, now let's calculate the mutual inductance. So M naught is, mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. That's mu naught. N is 600 turns divided by 0.55 meters. That's N is number of turns per meter. And area A2 is, that's the area of A2, times 1.1 into 1.4 centimeter square. We have to convert that to meter square, 4 meters square. All right, now let's go ahead and calculate everything. So this is 10 to the minus 11, and then we'll borrow 2 from there. That's 10 to the minus 9. So let me copy this. Okay, so 10 to the minus 9, 4 pi into 6 over 0.55 into 1.1 into 1.4. And this will be henries. That's M12. All right, so this is equal to Okay, so 211 nanohenry. Okay. Again, essentially, if the current, this is nanohenries. So if you look at this equation, this is what it means. If the current is changing 1 amp per second, the EMF induced in this guy is nanovolts. That's what that amounts to. Okay, so it's telling you the strength of the coupling. All right, so this problem says a solenoid 50 centimeters long is wound with 500 turns of wire. The cross-sectional area of the coil is 2 centimeters squared. What is the self-inductance of the coil? Okay, so they're asking you what is the self-inductance of this coil. And the self-inductance denoted by L is mu naught N square A times L. Okay. N is the number of turns per unit length, and this is the volume of the solenoid. Okay. Area of cross section times L. So little l is the length, and A is the area of cross section. So again, mu naught is 4 pi times 10 to the minus 7. N is 500 turns divided by 0.5 meters, and that's squared. The area of cross section is 2 centimeters square, and again length is 0.5 meters. Okay. So that's the self-inductance of this coil. All right, let's take care of powers of 10. There's 10 to the minus 4, and here's 10 to the 2 squared will give you 10 to the 4. So that'll cancel that. So we have a total of 10 to the minus 7, 4 pi, and the units will be henries into 25 divided by, oops, no, 5 divided by 0.5 is 10. 10 square is 100, so that's 100 into 2 times 0.5. All right, that's 1. And 4 pi is so that's 3, 5. Okay, so 0.126 millihenries. That's 0.126 times 10 to the minus 3, which is a millihenry. Okay? So that's the self-inductance of this coil. Again, if you guys remember, the self-inductance is the EMF induced is minus L di by dt. Okay, so what this number tells you is if current changes at 1 amp per second, if the current changes at 1 amp per second, the self-induced EMF will be millivolts. Okay, so 1/10 of a millivolt. Okay, this problem says a long cylindrical solenoid with 100 turns per centimeter has a radius of 1.5 centimeters. Neglecting the effects neglecting end effects, what is the self-inductance per unit length of the solenoid? Okay, so N is 100 turns per centimeter, and 1 centimeter is 10 to the minus 2 meters. So this is 10 to the 4 per meter. So the inductance is mu naught N square A L. And inductance per unit length is mu naught N square A. So we'll put in these things. So inductance per unit length, mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. N we just found out is 10 to the 4 per meter squared, and area is 0.015 meters squared. Okay, that's 10 to the minus 2 minus 4. That's 10 minus, minus 4 minus 11, and that's 8, so minus 3. So 10 to the minus 3. And units would be Henry per meter. Henries per meter. And then that's 4 pi times 1.5 squared. Oh, there's another pi, 4 pi squared. Okay. All right, so let's see. So this is 88.8 millihenry per meter. Okay, so what we're calculating is, so if the solenoid was long and the number of windings were the same, so what we're calculating is, this is telling you what would be the inductance, self-inductance per meter. Okay, so this kind of stuff is useful for coaxial cables and stuff like that, where you want to know the self-inductance per meter. Okay. Okay, so this problem says, at the instant a current of 0.2 amps is flowing through a coil of wire, the energy stored in its magnetic field is 6 times 10 to the minus 3 joules. What is the self-inductance of the coil? If you check your notes, you find that the energy of a coil is 1/2 Li squared. And again, so if this was the coil, the energy stored is in the magnetic field. Okay. Anytime you create an electric or magnetic field, you're storing energy. Okay. So that's where the energy is stored. Okay. So they ask you, what is the self-inductance? Self-inductance is 2U over I squared. So L, the inductance is 2. The energy stored is 6 times 10 to the minus 3 joules. And I is 0.2 amps. So this is 12 divided by so 12 divided by 4, which is 3/10. So that's the inductance of the coil. You guys understanding this? Yeah. Okay, so this problem says, how long after switch S1 is closed does it take the current in the circuit shown to reach half its maximum value? Okay, if this inductor wasn't present, you close the switch, the current would rise instantaneously to its maximum value. With the inductor present, what happens? The current rises exponentially. Okay? And so the maximum value is the same as that. Okay? What they're asking you is, at what time does it reach half its maximum value? Okay? And so after you close the switch at time t equal to 0. The current as a function of time is given by the maximum current is E over R, as if this guy wasn't even present. Okay, an ideal inductor has 0 resistance. It's E over R, 1 minus e to the power of minus t over tau, where tau is the time constant, and the time constant is L over R. Okay, so they want you to, so the current is half the maximum value, and again the maximum value is at t equal to infinity. This goes to 0. The maximum value is E over R. So half the maximum value is half E over R equal to E over R to 1 minus e to the power of minus t half over tau. Okay, so this guy cancels. Half is equal to 1 minus e to the power of minus t half over tau. Okay, and if you take the log, natural log of both sides, minus t half over tau equal to log of a half okay, and okay, so and log of t log of half is 0.69. Okay, so let me make some space here. And so t half works out to 0.69 okay. So again, when you close the circuit with the inductor present, it rises to half its maximum value in 70% of the time constant. Okay, 0.69 times the time constant. All right. So here's a similar problem. The current in the RL circuit shown below reaches half its maximum value in 1.57 milliseconds after the switch is thrown. Determine the time constant of the circuit and the resistance of the circuit if L is that. Okay, so T half we saw in the previous problem is 0.69 times the time constant, and t half is 1.75 milliseconds. Okay, so tau is t half divided by 0.69. Okay, so t half is 1.75 milliseconds. So the time constant is all right. So the time constant is that, and the time constant is related to L and R like this. So R would be L over time constant. L is 250 millihenry, and time constant is 2.54 milliseconds. And henries over seconds is ohms. So this is a little less than 100 ohms. Okay. 98.4 ohms. All right. We'll come back to this problem. This is that's a slightly involved problem, and I'll save it for last. You don't have to worry about that for the exam. Oops, that's a lot of pages. All right. This says, what is the self-inductance of an LC circuit that oscillates at 60 hertz when the capacitance is 10 microfarad? You guys learned that here's a circuit that oscillates. Okay, this is your basic tuning circuit, remember? And this circuit oscillates at a frequency, angular frequency given by 1 over root of LC. Okay. And omega, of course, is equal to 2 pi f. So what they're saying is this is 60 hertz. F is 60 hertz. Okay. So they give you this, and they give you the capacitance, so they ask you to calculate the inductance. Okay. So if you square that, 4 pi square f square equal to 1 over LC. So L is 1 over C 4 pi square f square. Okay. Okay, so this is capacitance is 10 microfarads. 4 pi square, and frequency is 60 hertz. Okay, so this is equal to 10 to the power 5 divided by 4 pi square into 3,600 henries. So this works out to 0.7 henries. So in this circuit that oscillates at 60 hertz, 60 times a second, the capacitance is 10 microfarads and the inductor is 0.7 Henry. Okay. Okay, so this problem says what resistance must be connected in series with a 200 millihenry inductor of the resulting RLC oscillating circuit if of the resulting RLC circuit oscillating circuit is to decay to 50% of its initial value of charge in 50 cycles. Okay. To 10% its initial 0.1% its initial value in 50 cycles. Okay, so what okay, so this guy, how long will this guy oscillate? If you charge this capacitor and let go, how long will it oscillate? I'm sorry? So this will oscillate forever. This is like a frictionless mass attached to a spring. What is the parallel of friction here? Resistance is the parallel of friction. Resistance is what converts good energy to bad energy, which is heat. Okay, so if you have a capacitor and you add a resistor to that circuit, this will also oscillate, except that this energy is dissipated, the resistance is dissipating the energy, and that's converting that to heat, and so the oscillations will eventually die out. Okay? And if you look at your notes, so so here's how the oscillations are dying out, and here's how the charge on the capacitor decreases. So Qt is Q max e to the power minus RT over 2L times cosine of, now this is the damped frequency. The frequency also changes. Okay, so the damped frequency is different than the frequency without the resistor. Okay? So Qt, the charge on the capacitor, changes like so. Q max e to the power of minus RT over 2L cosine omega damped frequency plus phi. I guess that's the phase constant. That's the damped frequency. And the damped frequency is okay. So there's the frequency, undamped frequency, and that's how the resistor changed the frequency. Okay. So what they're asking is, so I'll do just one part of the thing. What resistance must be connected? So what should the value of this resistance be such that this oscillating circuit is to decay to 50% of its initial value charge in 50 cycles. So this guy needs to drop to half in 50 cycles. Okay. Okay, so what you want is E minus RT over 2L to be 0.5. What is T? T is 50 periods, and 50 period, 50, yeah. And this guy is related to the frequency, so 2 pi F is omega D. Okay, so F is omega damped frequency divided by 2 pi. All right, so we'll put all that in there. Okay, so let's do this. So, okay, omega d. So T is 50 into 1 over frequency. Frequency is omega d over 2 pi. Okay, so there's omega d. I've substituted for f. That's t. Okay, so at this time, there's the time. You want e minus r t. T is this 100 pi. Okay, so what I'm doing is I'm bringing this equation in here. Okay, so, and I'm substituting for t. So what we want was e to the power minus rt over 2l to be 0.5. And I'm substituting for t there. There's t. Okay, this is a mess. All I want to do is show you this. L is given, C, so the problem didn't give C, so we had to, that was a typo, we had to give C. So L is given, C is given, and we know everything, so R is the only unknown, and you can solve for R. Okay? But obviously it's a mess, and so I'm not going to solve this, but I wanted to show you this. Okay, so what you would do is take the log first. Okay, so if you take the log, what you get is minus r by 2l into 100 pi, and in the denominator 1 over lc minus r over 2l square to the power half. Okay. And now you can solve for r. Okay. All right. Now we'll go to the last problem, and I'm just going to set it up for you. Again, this is a very long problem and it's messy. Okay, so let's look at the problem first. Okay, so here's we'll sort of use a Kirchhoff's rule. Okay, so when you close the switch, this current starts rising, and as the current in this thing rises, this thing fights it. Okay, it opposes it. This will act like a battery in this direction as the current is rising. Okay. Once the currents have reached steady state, okay, so this is an ideal inductor. Once the current have reached steady state, it's not changing anymore. This potential drop goes away. Remember that potential drop was minus L di by dt. In this case, I2. Once this has gone to zero, this potential has gone to zero. Okay? Okay, so once steady state reaches, this has become a short, and this current goes through here like that. There's no current over here because there's no potential drop across this. Okay? So in steady state, I3 will be zero. So I3 at infinity, at time t equal to infinity is zero. And I1 infinity is equal to I2 infinity. Okay. So after you close the switch, And after a long time, this current is equal to this current, and this current is 0. That's what we're saying. Okay? All right. Now, so in an inductor, okay, the way the current changes is, so in an inductor, I2t is I2 max times 1 minus e to the power of minus t over tau. Okay, whatever the time constant is of the circuit. That's how the current changes. Okay, this current will rise exponentially. Okay, at t equal to infinity, this was equal to I2 max, and I2 max is equal to, well, t equal to infinity is, okay, so at t equal to infinity, this will be 0, so the current will be I1 max, which will be E over R1. Okay, at t equal to infinity, this has gone to 0, this is the only current, and this is equal to, this current is equal to E over R1. I2 max equal to I1 max equal to E over R1. Okay. So I2t is equal to E over R1, 1 minus e to the power of minus t over, we don't know the time constant still. All right, so just looking at the diagram at t equal to infinity, we know what should be the currents. This current is 0, and this current is equal to this current. That's all we're saying. And here is the functional form of I2t. Okay. All right, now let's write down the equations. We'll use Kirchhoff's rules. Okay. We'll take this to be loop 1, this to be loop 2. Okay. All right. So loop 1, we are applying Kirchhoff's loop rule. Sum of voltages should add up to 0. Okay, so we'll start here. This is plus E minus, here's I1t R1 okay, and the current is I2t, and so since the current is increasing, this end will be positive, okay, and this end will be negative, and as you go across, you get negative L di2 t by dt equal to 0. So that's loop 1. Okay. And we'll write down the equation for loop 2. Okay. So loop 2, this is, we're going to start from here. L di2, this is plus L di2 by dt minus I3 R3 equal, I3 R2 equal to 0. So that would be L di2 dt minus I3t R2 equal to 0. All right, so here it is. Okay, so here's what we're going to do. We're going to use this I2 and substitute it in here. Okay, so let's call this equation 2, 3, 1. Yep. So we'll substitute 1 and 3. Okay. So what was 1? 1 was I2T. Okay. Let me copy this. Okay, so what we need is I2 is that, and d by dt of I2t is E over R1 times minus 1 over tau 2. Okay, so there's the derivative, and we're going to substitute that in here, in this equation. All right, so you can see that this is a messy problem. L di by dt, oops. L di by d2, here's di2 by d2 is this. Okay, so we'll put that in there. L times E R1 tau e to the power minus t over tau 2 minus I3t R2 equal to 0. Okay. At t equal to infinity, this goes to 0. This goes to 1. And we run into a problem. Something went wrong. So here's the problem. At t equal to infinity, this goes to 0. Oh, this goes to 0. Okay, so what did we do wrong? Well, this does go to 0. This goes to 0. That's fine. So what's going on? Okay. Oh, this goes to 0. Okay. Well, so yeah, this is fine. This goes to 0. This term goes to 0, and this term goes to 0, and that's fine. Okay. But it's okay. So from this equation, we can solve for I3t times R2 equal to L E R1 t2 e to the power of minus t tau 2. Okay. So I3t okay, now we got the functional form for I1t and I3t. Okay. And we had the functional form for I2t. So you can use that to get the functional form for I1t. So I1t equal to I2t plus I3t. Okay. And I2t was e over r1, 1 minus e to the power of minus t over tau 2. And I3t is L E R1 R2 tau 2 e to the power of minus t over tau 2. All right, so as you can see, this is messy. You have the functional forms of the three currents, and you have this limit at t equal to infinity limit, okay? And you can use all that to work it out. All right, we'll stop here. I'll